Hey, welcome to the next video in the Combinatorics series, ending the first section. I'm going to do a few exercises from the end of the section, in particular the first four. So the first problem is when rolling n dice, what is the probability that the sum is even? So this WITPT is my abbreviation for what is the probability that. Fairly straightforward question, although I found the solution quite hard to find. It took me more than a minute to think of this for sure. Now, once you know the trick, right, this basically, the solution to this can be found using a bit of a trick, but I think it's one that you really have to spend, at least I had to spend, quite a while coming up with the trick. So, if you're ready for the solution, right, you should probably think about it for yourself and try to come up with a solution, pause the video, come back when you're ready. But in any case, here's my solution. So the basic trick here is to realize that the first n-1 tosses of the dice don't really matter. One way or another, right, if you sum up to the first n-1 tosses, it's going to end with a sum that is either even or odd, but in either case, it doesn't matter because the probability that the overall sum is even will be 1/2, no matter whether the first n-1 rolls ended in an even sum or an odd sum. So, just for example, imagine that you rolled a 2 and then a 6 and then a 3, and let's say that we're talking about n equal to 4, so that we have one more roll. So the first n-1 rolls landed us on an odd number. Well, I have a 50-50 chance of getting an even, right, making the overall sum even because I have a 50-50 chance of the next roll being odd. But that would be true really no matter what this was, right? If this came out to an even number instead of an odd number like I've shown here, the same analysis would apply. You would just need to get an even roll if that sum came out even. So anyway, basically, no matter what the first n-1 rolls come out to be, it gets you, right, summing up to that point is sort of irrelevant because you're still going to just have a 50-50 chance no matter what happened that the next roll is going to make the overall sum even. And so the probability in this situation is 1/2. So very easy solution, but not at all obvious how you are supposed to approach that problem, in my opinion. Anyway, just in case anybody's curious, I've written up a slightly more formal argument that just kind of formalizes the more intuitive argument I just gave. So that's all that is on this slide. Okay, moving on to exercise 1.1.2. We want to count all of the rectangles which have positive area and are formed by segments in a grid of m horizontal lines and n vertical lines. So if we imagine that we have, let's say, 1, 2, 3, 4, right? So the number of vertical lines, m, is 4. And let's imagine that the number, sorry, did I say vertical? I meant horizontal. Anyway, and so the number of vertical lines is n equal to 2. Anyway, so how many rectangles could be formed in this way? Well, we would need to first choose a, basically, or actually, maybe this is too small because it's a little hard to even see what's really going on. So let's maybe take n equal to 3. And then you can see that of the 4 horizontal lines, I need to choose 2. And it doesn't matter which one, without repetition, right? Because if you chose the same horizontal line twice, you would have area 0. So we need to pick 2 distinct, right? Cannot do it with repetition. So choose two distinct horizontal lines from the available four without order, because picking this one and that one, you get the same rectangle if you did it the other way around. So effectively, that means that the number of ways of choosing two of the available four horizontal lines is 4 choose 2. So 4 choose 2. That's the number of ways of picking the horizontal lines, and then for every choice of horizontal lines, we get a new batch of rectangles by every choice of picking 2 vertical lines out of the available 3, so that's 3 choose 2. And more generally, of course, m choose 2, n choose 2 is the general solution for all of the possible rectangles. So I've basically just written that on the slide, and we can move on. Okay, exercise 1.1.3. The Roman alphabet has 21 constants, 5 vowels. How many strings can be formed using R constants and S vowels, right? So this is a little bit like things that we've seen already in a few videos. The basic idea is that we know that we're going to have, let's maybe diagram it as some number of constants. So I'm going to start, right, this is just an initial diagram, but I've got maybe like constant, 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 constant. There are R of them. Vowel, 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 vowel. There are S of them. And so there are a few things to consider here, right? The first thing to consider is that each constant can be chosen in each consonant can be chosen in 21 different ways. The vowels can be chosen in 5 different ways. So even if the consonants and the vowels occurred in the order that I have described them here, we would effectively get 21 choices for each one of the consonants, 5 choices for each of the vowels. We're using the product principle here, so that you would effectively get 21 to the R, 5 to the S as the number of words. Right, so this would be the number of words if the consonants and vowels were arranged in this particular way, but for every possible rearrangement of locations of consonants and vowels, we get, more choices that way, I guess you could say. So in any case, we then multiply this, right, by 21 to the R, 5 to the S, times the number of possible rearrangements. And the number of possible rearrangements is going to be, well, it's a word of length R plus S, and we would like to choose R of them to be the consonants. So, in effect, the number of ways of rearranging the C's and the V's is 21 plus 5. Choose 21. We could also have said choose 5. We'd get you the same thing. But anyway, so there's the solution to that one. On to exercise 1.1.4. We have an election with 30 voters and 4 candidates, and we'd like to count all possible outcomes, which I take to mean the number of ways that basically votes could get distributed to candidates, right? So that almost kind of gives away the solution, but pause and come up with it yourself. It's basically stars and bars, right? So the candidates the votes are the stars, and the candidates are the bars, right? The votes are going to these bins which belong to the candidates. And so, so we've got 30 stars, and then the bars are 4, so we use 30 plus 4 minus 1 in the formula for the, I'll just display it right here. So 30 stars plus 4 minus 1 bars. We're using the stars and bars formula where a particular bin could receive 0 because that seems to match this situation. So, and then we choose the number of bars, which again is 4 minus 1. So, so that's the solution to the first part. Now, the second part asks us to count those in which no candidate receives more than half the votes. I found this substantially tricky. And so, all right, so trying to sort of build up toward the solution, one thing you can realize, I mean, of course, right, if we're saying that there are 30 votes and we want no candidate to get more than half, then we're saying nobody gets more than 15, right? Nobody gets 16 or above. And so, to begin with, you know, it does seem just easier to count up everything, which we've already done. That was the answer to the previous part. And then subtract away the things we don't want, because the things we don't want, right, where some candidate gets at least 15, seems, or sorry, at least 16, seems easier. So, right, because it gives us an assumption, it gives us, you know, something that we know about what happened that we can kind of work with. So, even from that realization, it's still not clear what we do next. One thing that we realize we can do is we will effectively want to have this variable y, and we'll take x1 to be 16 plus y. So y now can take any number, right? Like by doing it this way, we kind of guarantee that x plus 1 will take at least 16, possibly more. So in a sense, x1 is the candidate who gets strictly more than half the vote. And y is now free to range from 0 up to 14, really, right? Because we're already ensuring that x1 gets 15, so 16, so that leaves only 14 votes for the remaining variables to fight over. And so we'll now look at y plus x2 plus x3 plus x4 equal to 14. Now, this is assuming that the first candidate is the candidate who receives more than half of the votes. We could repeat this all over again for the second candidate and so on. And what's really important to realize is that these possibilities are disjoint. So I'm now using the sum principle where disjointness is important. If one of the candidates is the one who receives more than half, then no other candidate could as well. And that is why I am free to just multiply by 4 in my solution, right? So I take 14, which is the remaining votes, plus 4 minus 1, because that's the number of bars in my stars and bars. Choose 4 minus 1, again, that's the number of bars. And I multiply by 4, and that multiplication by 4 is valid because each of these scenarios is disjoint, and they are, right, you can count them up with exactly the same formula. So I can just add them all together, and it's the same number added 4 times. So you might as well multiply by 4. And again, importantly, if we didn't have the constraint that we were talking about, strictly more than half, so that no two people could do that at the same time, you know, if we didn't have that, this solution technique wouldn't work, and it would be a much harder problem. And here I've just written up a slide basically reiterating what I've already sort of maybe even overemphasized.